Hello everyone. Today I will be showing you a demonstration of one of our projects at the Center of Autonomic Computing at University of Florida. This project deals with running time-sensitive applications correctly on virtualized platforms. To give a little bit of background, many of the applications that we run are what is called best effort applications. The words best effort imply that while we would like these services to execute as fast as possible, a slower execution due to limited resources would not make the service incorrect or useless. There are, however, other applications that are called time sensitive, meaning that unless some amount of processing happens before the end of a real world deadline, the execution is considered wrong. As for example, consider a financial application that expects some input within X seconds after a query has been sent. If the reply comes after this time, the query has already timed out and the execution does not result in any desired output. One way to ensure correct execution of similar time-sensitive applications is to make sure that sufficient resources are available to these services so that they are able to meet their deadlines. Currently, most operating systems use fair share or proportional scheduling schemes to distribute available resources between running applications. These schedulers have the goal to maximize full system throughput and do not have provisions to adapt to time-related requirements of individual applications. In our research, our aim is to monitor the performance of time-sensitive applications, compare this performance to a set desired reference, and dynamically reallocate resources to applications to make sure that deadlines are met. We have developed a cross-layered architecture to be able to do this. The way this works is as follows. We have a small daemon routine that runs in the background on virtual machines and records instances of time-sensitive processes. This routine communicates the performance and deadlines with a control structure running on the control domain, also called domain 0 in the Zen vocabulary. This controller has a global view of all the time-sensitive processes running on all the different domains, and it intelligently reallocates resources to be able to meet all the deadlines. The resources that can be tweaked by the APIs present on the control domain are wait, cap, and memory. Let's now jump into the actual demonstration. On the following page, you will see a brief introduction of the project. In the two boxes that will show up in some time, we show a test application called GLX-Cares. The application is part of the MISA utils library that we have modified, and the source code is available and can be downloaded from the links at the bottom of this page. This demonstration was developed using Zen Virtual Machine Monitor. We are using two identical domains, each running one instance of modified GLX-Cares and some other background processes. The left window shows an instance of GLX-Cares that is running as a time-sensitive application, meaning that its performance is being monitored and dynamically compensated for by the controller, while the one on the right is running a best effort application. Here we are using frames per second rendered on the screen as the input reference. In addition to these two applications, we are also starting background processes every 10 seconds to create CPU contention. You can clearly see that there is a considerable qualitative difference between the outputs of the two GLX-Cares instances. The demonstration further shows plots of frames per second at the bottom of this page. Here, the top two lines show frames per second on the left and the right GLX gears instances, and the red plot towards the bottom shows the controller action, which in this case is reallocation of weights to the domain running the left instance of GLX gears. There are two pertinent observations to be made. One, from the green plot we can see that the frames per second on the controlled GLX gears instance are closer to the desired reference. And two, the frames per second of the controlled GLX gears, in this case the green plot, has much less jitter and is much more steady than the one that is not controlled, which is the violet plot. From the controller actions seen in the red plot at the bottom, we see that the domain resources are reassigned every once in a while. So in conclusion, we see that the controller in the background can improve the performance of time-sensitive applications. The approach suggested by our work here requires minimum changes to the virtual machine monitor code and is completely transparent to the virtual domains. In future, we plan to explore other control strategies and control knobs to further improve the performance of our applications. That's it. Thanks for listening.